For number 2 here, let's start it with the auxiliary equation. That's the most important part of the problem. Okay, m squared plus 2m plus the lambda plus 1 equals 0. To solve this quadratic equation, so m equals negative b plus minus square root, because we don't know what lambda is, right? So the quadratic formula is the option to find the solution of the m for this case. So m equals negative 2 plus minus square root of the m squared, which is the b squared, which is 4 minus 4ab. So 4 times 4ac, sorry, 4 times the lambda plus 1 divided by 2 times 1. We write it as negative 2 over 2, that's 1, negative 1, plus minus square root. So this is 4 minus 4 lambda and minus 4. 4, negative 4 gone, this divided by 2, right? So now becomes negative 1 plus minus square root of negative 4 lambda, which is 4 square root negative lambda. Square root 4, sorry, or the 2 square root of negative lambda. 2 divided by 2, that becomes negative 1 minus 1 plus minus square root of negative lambda. You guys okay? Yeah? All right. So this is more complicated case. So since m equals negative 1 plus minus square root negative lambda, negative lambda is the one that gives you what case that you're going to get the solution. Case 1, case 2, or case 3. So case 1. So the two real roots, two real solution. Or we have to see the negative lambda as positive number, or the lambda less than 0, right? So then the m going to be negative 1 plus minus the real number. Again, in the square root, we're going to use the convenient number as omega squared equals negative lambda. Again, negative lambda positive, omega squared must be positive by default. If the omega squared is negative lambda, so then the m going to be negative 1 plus minus omega. Okay? Or negative 1 plus omega, negative 1 minus omega as two options of the two solutions for the m. Then the general solution is y equals, let's see, 1 e to the negative 1 plus omega times x plus c2 e to the negative 1 minus omega times x. Same routine. And with the conditions y at 0 equals 0, y at 5 equals 0. This time for the x0, we get y0, e to the 0 is 1, e to the 0 is 1, almost the same pattern as before. So c1 equals negative c2. For y at 5 equals 0, 0 here, and the c1, this is kind of the messy part, c1 e to the negative 1 plus omega times 5 plus c2 e to the negative 1 minus omega times 5 as well. From c1 equals negative c2, factor c2 out, you get negative e to the, if you multiply it back in, like the 5 in, right? So it's going to be negative 5 plus 5 omega plus e to the negative 5 minus 5 omega. Same analysis as the previous example. The exponential will not be 0, and always greater than 0, always greater than 0 for the exponential part. Okay, and then what we could do, since these two quantities will not be the same because the omega itself is positive, omega positive. If omega is 0, you can cancel these two e out, Since omega positive, so the sum of these two e, or the one negative, one positive side here, will not be zero. Will not be zero. If it not be zero, it's gonna force C2 again to be zero. If C2 is zero, C1 gonna be zero. Typically, the case 1 here gonna be the case to give you the trivial solution. What I'm looking for when you do the homework or do the exam, I'm looking for the auxiliary equation solution. For the detail for each case, you have to prove it to me that case 1 trivial. Why is trivial? After you use the boundary conditions. Okay. And then case number 2, the case that you have the repeat root or repeated solution. From m equals -1 plus minus square root negative lambda to get the repeated roots, that means you're gonna make this to be 0 or the lambda equals 0. If lambda equals 0, the m gonna be -1 and -1. So then the general solution for case 2 is y equals c1 e to the negative x plus c2 e to the negative x and then multiplied by x. Okay. Two conditions, y at 0, y at 5 equals 0. The first one, 0, 0, we get c1, 0. For y at 5, y equals 0. c1 is already gone, that term gone. And you get c2 e to the negative 5 times 5. These two not 0. 5 is very clear it's not 0. Exponential never be 0. For c2 to be 0 again, c2 0, c1 0, another trivial solution. But not all the cases the lambda equals 0 gonna be gonna give you the trivial solution. So you have to analyze because it's totally based on the boundary conditions. All right, case 1, case 2 don't work. Case 3 always work. That's the case that the eigenvalue, eigenfunctions come out. Okay, this one, you're gonna look for the conjugate complex solution. Okay, so m equals -1 plus minus square root negative lambda. So we're gonna need the lambda to be positive, right? To get the square root of negative side or get the complex conjugate out. So then we're gonna let omega square be lambda. So the m equals -1 plus minus square root of negative omega squared or -1 plus minus omega times I. And will give us the general solution as y equals, this time we have the real part, e to the negative x, and the imaginary part gives you the sine cosine term. So c1 cosine omega x plus c2 sine omega x. All right. So after this, we just work on the conditions, y at 0, y at 5. At 0, e to the 0 is 1, cosine at 0 is 1. And at 5, y equals 0. Ignore the c1 term, that's gone. So e to the -5 times c2 times the sine at 0, no, sine at 5, sine at 5x. I keep saying about the condition at 0. So the second condition here, x equals 5. Now this is 5 omega. Okay, 5 omega. So with this, exponential, not 0, or always positive. For the non-trivial solution, non-trivial, solution, or the case that y not equal 0. So we're gonna need C2 not to be 0. Okay, if C2 not equal to 0, psi 5 omega must be 0, because that's a product to give you the answer 0, right? So psi of 5 omega equals 0. We're gonna, same as the last example, what angle 5 omega that makes psi to be 0? Another sensitive case that I always said, and I also said in the previous case, since omega is positive, right? The angle must be positive quantity. So gonna be the n pi again, like last time, not including the 0 angle, gonna be starting from pi, 2 pi, 3 pi, and so forth. So 5 omega is the n pi for n equals 1, 2, 3, and so forth. So the omega is 5 pi over, no, n pi over 5, sorry. N pi over 5 for n equals 1, 2, 3, and so forth. From the relationship of the lambda, which is the eigenvalue, and omega is omega squared. So the lambda n, subscript n, is omega squared, which is n squared times pi squared over 25 for n equals 1, 2, 3, and so forth. Now, you have the options to get the non-trivial solution by selecting whatever the value of the n. N1, you get one eigenvalue. N equals 2, you get another eigenvalue, and so forth. So this is the eigenvalue. And then the eigenfunctions associated to eigenvalue, eigenfunction, oops, too far. Yn equals, back to the general solution that what we got earlier, where I went too far right there. So the general solution here, bring it to this form, ignore the C2 because C2 is just the condition, not the condition, the parameter that, or the constant multiple to the fundamental solution of the differential equation. So ignore the C2. So the core piece of the solution will be based on the psi function. So Yn is psi omega. Omega is n pi over 5. So going to be 5. It's going to be n pi over 5 times x. So that's what we are looking for. The goal is to find eigenvalues, eigenfunctions, satisfy the boundary condition. So that means you can pick the options of the relationship of the numbers. Like for this case, you have 3 terms, right? You have, let me explain more about the equation. We have y double prime plus 2y prime plus the lambda plus 1 times y equals 0 for the spring based on the m y double prime plus the beta, which is the damping constant, the beta times y prime plus the k times y equals 0. When you rearrange, so this is y double prime plus the beta over m plus k over m. This is y prime, and this is a y equals 0. So that means you see the relationship of the beta and m as true. Beta is a damping force, damping constant, the m is the mass, k over m equals the lambda plus 1. So you can pick the lambda based on the, or when you pick the lambda, you can use to pick the option for the k and the m.